the normal distribution is a lot of times called like the bell curve because it sort of looks like a bell shape. And the idea is the normal distribution describes the probability density assigned to each of the possible outcomes for a continuous random process. So a lot of things in the natural world are either continuous random processes, or you could approximate it using a continuous random process. And while in statistics there's a whole bunch of different distributions that describe different situations, a lot of those distributions, if you take a whole bunch of copies of them and then add them together, then the resulting sum is actually a normal distribution. So that's called the central limit theorem, and I don't want to get into like a whole bunch of statistics. I'm not going to test you over anything that has to do with statistics. But what I'm trying to say is that this is really important for statistics, and statistics is really important for science. And so this particular formula has a whole lot of importance in general. So what you're looking at whenever you're looking at a bell curve, or you're looking at the normal distribution probability density function, is on the vertical axis probability density, and on the horizontal axis, the horizontal axis represents all of the possible outcomes of a random process. So like as a silly kind of example, maybe you're out in the desert and you're looking at a particular species of lizard, and you capture a bunch of lizards in the desert and you measure the length of the lizard's tail. And so maybe the mean length of a lizard's tail is like 5 inches long. And you might say that the mean is 5 inches, and then you might also want to know about the standard deviation, or how well dispersed are the data of the lizard's tails. If almost every lizard has a tail length of almost exactly 5 inches, we would say that the dispersion of the data is small and the standard deviation of the measurements is small. But if the lizards have tail lengths that vary wildly between 0 inches and 10 inches, then you would say the standard deviation is really large because the data is very dispersed among the possible outcomes. But anyways, the length of a lizard's tail is approximately normally distributed, and so the probability density function would look something like a bell curve. And I'm not a great artist, but that's supposed to represent the normal distribution. If you actually want to talk about probabilities and not probability density, then for a continuous random variable like this, you would have to say, okay, what's the probability that the next lizard that I capture has a tail length that falls somewhere in between 5 inches and 7 inches? And then the answer to that question, what's the probability that the next lizard I catch has a tail length between 5 and 7 inches? This is the area under this curve. And so the area under the curve is what we would calculate using an integral. And so by taking the integrals of the normal distribution probability density function, we can calculate probabilities. So the area under a section of the curve represents probability, but it's also important that if you're talking about a random process, the sum of the probabilities of all possible outcomes must be 1, right? It wouldn't make any sense at all if I told you that, like, I've got a coin, I'm about to flip a coin, and there's a 60% chance it'll land on heads and a 60% chance it'll land on tails. That would be stupid. That would be a 100% chance that it lands on heads or tails, but you know that the sum of the probabilities of the two possible outcomes, they have to add up to 100%. Or in other words, they have to add up to 1, okay? So in the case where we have a random process with a continuous random variable, what that means is the integral over the entire range of possible outcomes of my probability density function, that has to be 1. Okay? That's the equivalent statement for continuous random variables. Then if I take this formula and I pop it into my integrand, then this is going to look like the integral of 1 over sigma square root 2 pi e to the power negative 1/2 of x minus mu over sigma all squared dx. Just making sure I copied it correctly. Okay, yeah. And then for the normal distribution assumes that your random variable could take on any value from negative infinity to positive infinity. It just assumes that your random variable could take on any real value. So if I want to add up the probabilities of the entire range of possible outcomes, I have to integrate from negative infinity to plus infinity. Okay. So that means that since the sum of my probabilities has to be equal to 1, that integral has to be equal to 1. All right. So you might notice by staring at this integral that if we select a mean for our distribution, so the mu just equals some constant number, and we also select a standard deviation, sigma, and so sigma just equals some constant number, then this whole chunk out front is just a constant. I mean, it's a constant with respect to x anyways, and that's what I'm integrating. So I could pull that outside of the integral and then multiply both sides by sigma square root 2 pi. And if I do that, then it says the integral from negative infinity to plus infinity of e to the power negative 1/2 x minus mu over sigma all squared dx is equal to sigma square root of 2 pi. So here's what I'm trying to get to. Here's what I'm trying to get at. Somebody at some point had to discover this formula. And whenever they were discovering the formula, you can ignore the constant for a second and just look at the e to the negative something squared. The e to the negative something squared, that's what gives you the shape of the normal distribution, right? So I want Desmos. So if I just wanted to show you the shape of this normal distribution, I just have to give you y equals e to the negative x squared, and then that's the shape of it if I don't care about the actual values, right? That's the bell curve already. So the shape part gets nailed down by this function, and then the question is, whoever discovered this formula, why did they know to put this constant in front of the exponential function? Well, they knew because they wanted the integral of the whole thing to be equal to 1, but that means they had to know that the integral of this without the constant would be equal to sigma square root 2 pi. And so that's what I'm going to show you today, is I'm going to show you how you would integrate this and figure out that the integral is sigma square root 2 pi. In other words, whoever figured this out the first time, how did they know that this was true? So the first thing I want to do is a little substitution. And for my substitution, I want to say that u is going to be equal to x minus mu divided by sigma. So if I say this, then the derivative of u with respect to x is just 1. No, sorry, 1 over sigma. And so that means that dx can be replaced by sigma du. And so I could rewrite this integral in a little bit simpler way as e to the power negative 1/2, oops, it's supposed to be a half, negative 1/2 u squared times sigma, which is just a constant, du. But I hope you guys remember from Calculus 2, there's not an antiderivative of e to the power negative x squared, or e to the power negative half x squared for that matter. There's not an antiderivative that we can express in terms of just normal, everyday elementary functions. Okay? So there's numerical methods, right? You could use like Riemann sum, or you could use Simpson's rule, or you could use power series to figure this out, and you'd end up with a numerical answer. But I don't want to end up with a numerical answer. I actually want to figure out the analytical answer to this. Is there a way that you could be clever about this, not just with today's computers, but also like 100 years ago or 200 years ago, and figure this out anyways? So I need to remember this. It's going to be sigma integral of that. Okay. Okay, so this is what I'm trying to find the value of. So I'm going to go ahead and say this is equal to capital I. Capital I, just the value of my integral. Then if I multiplied this whole thing times this, you would agree that this second integral has exactly the same value, right? All I've changed is the symbol I'm using for the variable of integration, but in the end, once I evaluate the integral, the u's are going to go away and the v's are going to go away, and it's going to have the same value because it doesn't really matter what symbols I use. So this would now be I squared, because I'm taking the integral I want to know the value of and I'm multiplying it by itself, essentially. So I'm squaring it. But with regard to the first integral, where I'm integrating with respect to u, the v's would be constant. Okay? And with respect to integrating with the v's, then the u's would be constant. And so it's okay if I take this current constant over here, which is outside the first integral, and I just slip it into the first integrand. Just kind of like you can take constants out of an integrand, you can also put the constants back into the integrand if you wanted. And so if I do that, I'm going to collect my sigma squareds on the outside right now, and then I could form this where I've taken that second integral and I've just put it inside the first integral's integrand. Actually, maybe I skipped a step, so I'll take this a little bit more carefully so as to not confuse anybody. That'll be my next step. But here, what I'm trying to do is this. So here's that second integral again. Okay. Does everybody see how the second integral got pushed inside the integrand? Okay. So now, again, I'm going to rewrite what I just wrote, but this time without skipping that step. I'm going to take the sigma out because that's a constant. And then I've got e to the negative 1/2 v squared. But again, since this integral in the middle is integrating with respect to v, then u would be constant. And if u is constant, then this whole exponential function is also a constant. So I could put that inside that integrand as well. We can go ahead and just combine these guys like so. And this is from negative infinities to plus infinities. Okay. So, does anybody see what we're going to do next?
I will want to exponential v squared plus u squared.
Yeah, I can combine those exponential functions, right? There's a certain property of exponents that says if I'm multiplying two exponents with the same base, I could just add their exponents, right? So that would be the same as x to the 5th, for example. Okay, so that means I've got the same base, so this could just be e to the power negative half v squared plus negative half u squared, and I could factor out the 1/2, and I would get u squared plus v squared dv du. Okay. So far, so good. And now we're going to do a trick we learned yesterday in class, which is we're going to convert to polar coordinates. So my polar unit conversion is going to be where the horizontal axis is the u-axis and the vertical axis is the v-axis. If I say r is the distance from the origin and theta is the angle from the positive u-axis counterclockwise, then all of the old formulas still apply, including r squared is equal to u squared plus v squared. And what we learned yesterday is that dv du would be equal to r dr d theta. So if you weren't in class yesterday, I did upload the recording of that video this morning, and so you can see why the r dr d theta shows up. But this little r that we get from the polar unit conversion is going to save our lives here. It's going to allow us to write e to the negative 1/2 r squared r dr d theta. But then I have to change my bounds of integration because, you know, I'm doing a change of variables. So in terms of my radius is allowed to go from the origin out to infinity, so that would be from 0 to plus infinity. And then in terms of my angle theta, I want to be able to rotate all the way around my domain, so I'm going to let that go from 0 to 2 pi. And hopefully you can see that that region, which is the whole plane in polar coordinates, is equal to the region which is the whole plane in rectangular coordinates, from negative infinity to positive infinity for x and y variables. Okay, so still integrating across the same region, this time in polar coordinates. Now I can do a w substitution, because I've already used u. And this time I'm going to say w is equal to 1/2 r squared. So that means the derivative of w with respect to r is going to be 2r, which means I could replace the dr with 1 over 2r dw. Okay, so that's what I'm going to do. Hopefully, things are starting to wrap up.
Wouldn't this be 1r, not 4?
Oh, you're right. Yeah, good job. Steven's always correcting my mistakes. I really appreciate it though, because it's gonna make things easier. Very good. So theta is still going to go from 0 to 2 pi, and then I'm changing r to dw. And so the 1 over r is going to cancel that r, and then if I use this formula, of course plugging in 0 for r is 1/2 0 squared, so the lower bound is still 0, and plugging in infinity for r is going to give me 1/2 infinity squared, which is still plus infinity. Now my integrand is e to the power negative w. So this is looking like something we can solve. And this will be the integral from 0 to 2 pi of, and this has an antiderivative name of negative e to the power negative w. So e to the power negative infinity would be 0. As you go out to the left, the exponential function gets closer and closer to the x-axis. So in the limit, that would be 0. And e to the power 0 is just 1. And so we've got a situation where that integrand is just 0 minus negative 1. And 0 minus negative 1 is just 1. So then I take the antiderivative, it's just theta, and you plug in 2 pi and you plug in 0, and you just get 2 pi. So this is sigma squared 2 pi, which means what I was trying to find all along, that capital I, which was the value of my integral, is going to be sigma square root 2 pi. So that's how, for those of you that are coming in late, that's how we ended up with this 1 over sigma square root 2 pi constant in front of our normal distribution probability density function, is because we wanted the integral from negative infinity to positive infinity to be the number 1. But of course, if I only paid attention to this exponential function, we didn't get the number 1. We got the number sigma square root 2 pi. And so in order to get the number 1, we just have to multiply by the reciprocal, and then we get it exactly how we want it.